Hi, I'm Fergus Kelly, and for my project, I created a car telemetry system. In this final project demonstration video, I hope to explain to you the design of my system and how exactly it works. But first, some background. For this project, I've created a system that gathers and displays data from my car, a 2005 Toyota Prius. The system connects to the car's electronic control units via its internal network and requests specific parameters such as engine RPM, speed, and coolant temperature. This kind of system is made possible by the OBD2 and CAN standards. By law, every car manufactured in the United States since 1996 must comply with the Onboard Diagnostics 2 standards. OBD2 specifies a 16-pin connector, usually located under the dashboard, and a series of protocols and message formats for retrieving diagnostic and emissions data. My system connects to the OBD2 connector and uses parameter IDs specified by the standards to request specific types of data from the car's ECUs. Each ECU in the car communicates with the others using the CAN bus, so nearly all the data produced by the car is available on that bus via the OBD2 connector. However, although the CAN standard specifies the physical architecture and protocol for communicating on the CAN bus, each car manufacturer has a proprietary message format which can make receiving the data difficult. Therefore, my system connects to the CAN bus through the OBD2 connector, but is designed to access only the data made available through the standard OBD2 parameters. Here's the hardware I used to build my system, and I'll explain how it all fits together in just a moment. So here's the big picture of how the system works together. The car's CAN bus is connected to the UART via the OBD2 connector. The UART contains a chipset that converts the CAN messaging protocol to standard RS-232 serial communication. The FTDI board provides serial communication over USB to the Raspberry Pi. Altogether, this system allows software running on the Raspberry Pi to freely send and receive data from the CAN bus. This is what the system looks like assembled before it's connected to the car. From left to right, you can see the black OBD2 cable, the UART board and the smaller attached FTDI board, the red USB cable, the Raspberry Pi, and finally the portable battery to power the Pi. For the software side, I wrote two programs that provide telemetry functions. Both run on the Raspberry Pi or any other computer connected to the UART. The first, called OBDlog, is a command line utility written in C. It configures the serial connection in the UART and then repeatedly pulls the CAN bus by sending data requests to the UART. It can either immediately output or log the retrieved data. Command line options are used to specify the behavior of the program. Since multiple instances of OBDlog communicating with one UART would result in destructive behavior, a semaphore file is checked when the program runs. If the file already exists, the new OBDlog instance sends an interrupt to the previous instance. The previous instance can then close gracefully and the new instance can proceed. Here's an example of OBDlog in use. The first line shows the command to run OBDlog with certain options. Dev TTY USB 0 is the serial port the UART is connected to. 010C is the OBD2 parameter to request engine RPM. The final two options specify a 500 millisecond delay between requests and that the polling should occur for a 30-second duration. The output of the program is shown below. Lines beginning with a hash are informational comments that can be ignored. Each of the following lines are a data point with comma-separated columns representing the timestamp in milliseconds, the requested parameter, and the responses from each of the ECUs. Only the first ECU response column is shown here. By saving the OBDlog output to a file, we can parse it with other software. Using Microsoft Excel, I made this graph of engine RPM data captured while revving the engine for a short period of time. The second piece of software I wrote for this project is called OBDlogNet. It's a browser-based front-end for OBDlog which displays parsed data in real time. OBDlogNet can run locally on any computer connected to the UART, but for my system, I wanted any user to be able to access the real-time data wirelessly. To this end, the Raspberry Pi connected to the UART creates a wireless network. By connecting to this network and pointing their browser to the local IP address of the Pi, they can access the OBD LogNet frontend on their own device. Finally, let's see the whole system in action. I know the video is a little shaky, but you can see OBD LogNet displaying the speed on my laptop screen. Compare it to the car's speedometer on the left. While they aren't perfectly correlated, you can see they are quite similar. The laptop is connected to the Raspberry Pi's wireless network. The Raspberry Pi is using the OBD log command line utility to request data from the car's CAN bus, parsing that data into a readable format, and then sending it to the browser running on the laptop via WebSockets. As you can see, all the parts of the system are working together to gather and display the data. Thank you for watching. Once again, I'm Fergus Kelly.